right, so number 1 says which letter has vertical line symmetry? So we're looking for which letter we can go straight down. So remember, vertical lines go up and down. All right, so which one of these can have that line of symmetry? And hopefully you guys can see that the A would have that. So if I draw a capital A and I go down with a one vertical line, the left side of that A would match up with the right side of the A. And so 3 has vertical line symmetry. Number 2, which letter has vertical but not horizontal? So we want the same vertical line symmetry, but I don't want to be able to chop it left to right. Okay. X actually has both lines of symmetry. If I draw you guys an X, it has vertical and it has horizontal. Okay. O also has vertical and horizontal. V has vertical, but no horizontal, so I think that's our choice. E has just horizontal. Okay. Number 3, what kind of symmetry does the name Otto have? And we can't go horizontal because the tops of the T's wouldn't match up. But I think I can go vertical, and the T would match up with the T. The O would match up with the O. And so it has only vertical line symmetry. All right. Number 4 says, what is the total number of lines of symmetry in a rectangle that is not a square? So we're going to go ahead and draw a nice long rectangle to make it not look like a square. All right, so that's a rectangle that is not a square because not all sides are equal. And we can definitely go down with a vertical line of symmetry. We can go across for a horizontal line of symmetry. But I don't think that we could do a diagonal line. I don't think our rectangle would fold up on a diagonal line to match up its corners. You see that? Okay, sometimes you can try with like a piece of paper. A piece of paper, standard sheet of paper is a rectangle that's not a square. So that would work. All right, but a rectangle that's not a square is only going to have 2 lines of symmetry. If that rectangle was a square, then it would have 4. Okay. All right, going down. All right, so rotational symmetry is something else we have to talk about. Instead of just lines of symmetry, you could be able to rotate something and have it look like itself. And if the figure maps onto itself after a rotation of more than 0 degrees, but less than 360 degrees, then it's said to have rotational symmetry. All regular polygons have rotational symmetry because all the sides are congruent, and so are actually the angles of regular polygons. Okay, so it says finding the degree measure of rotational symmetry. How many ways can the figure sit there and look the same? All right, so we're going to find the degree measure of rotational symmetry of this picture. It says how many ways can the figure sit there and look the same? Okay, so because this looks like a regular 1, 2, 3, 4, 5-sided, this is a pentagon. A pentagon has 5 equal sides. And so that's why they're saying that you can turn this picture, and when you put another equal side down here on the bottom, then you wouldn't know that I turned the pentagon. And so I could go ahead and have DC on the bottom, and that would be one way. I could put, what is that, a B? Yeah, BC on the bottom, and that would be a second way. I could turn it so that AB is on the bottom. That'd be a third way. I could turn it so AE is on the bottom, and that would be a fourth way. And I could turn it so that ED is on the bottom, and that would be a fifth way. Okay, so there's 5 ways this picture can sit here and look the same exact pentagon that we started with. And so there are 5 ways. And then it says the degree of rotational symmetry is 360 degrees divided by how many ways it could sit there and look the same. So if we take 360 and we divide it by 5, we would end up with 72. And what that means is that it's every 72 degrees that I turn this. Okay, and 5 72s would go in a circle because that would be 360. And so every 72 degrees I turn it, this pentagon would look like himself. So if I did 2 turns of 72, that would be 144 degrees. 3 turns of 72 would be 216 degrees. 4 turns of 72 would be 288 degrees. And 5 turns would be 360. All right, and we'll try the next one. All right, so number 5 says, which regular polygon has a rotation of 252 degrees to carry the polygon onto itself? So here's what we're going to need to do. So in this first one, we have an octagon. An octagon has 8 sides. And since this is going to be a regular octagon, all 8 of its sides will be equal. And so there's going to be 8 ways this octagon can sit here and look the same. And so we're going to take 360 degrees and divide it by 8. And by doing that, we're going to find the minimum degree of rotation symmetry that this has. And so it's going to give us 45 degrees. And so 45 degrees, I could turn an octagon. 2 turns of 45 would be 90, and the octagon would still look like itself. Okay? 135 degrees. 180. Another 45 would be 225. Another 45 would be 270. Another 45 would be 315. And our last 45 would put us right back to 360. And you can see, guys, that we didn't say 252 at all. So it's not an octagon, but those are the degree of rotation symmetry that an octagon has. All right, let's go to a square. A square has 4 equal sides. And so 360 degrees divided by 4 is 90 degrees. So every 90 degrees you turn a square, the square would look exactly the same as how it started. And so this one's a little bit easier, but there's his 4 degrees of his rotational symmetry. And you're going to see that 252 is not one of them. And so we're going to move on. Okay, next one up is the hexagon. A hexagon has 6 sides. How I tell my son to remember that hex has x, 6 has x. Okay? And so if I take 360 degrees and I divide it by 6, I'm going to find out his minimum degree of rotational symmetry, which ends up being 60. So every 60 degrees I turn a hexagon, he'll look exactly the same. So 60, 120, 180, 240, 300, and 360. And you're going to notice we didn't say 252. So I'm hoping it's a decagon. Decagon, like a decade, is a period of 10 years. A decagon has 10 sides. So if we take 360 degrees and we divide it by his 10 equal sides, we're going to end up with 36. That is the smallest number of degrees you can turn a decagon and have him look like himself. And so we're going to do increments of 36. So 36, 72, 108, 144, 180, 216, 252. There it is. So that's the number we were looking for. If we keep going, you could also turn a decagon 288 to look like himself, 324 degrees, and then finally 360 would put him right back on himself, and he'd look exactly the same decagon that you started with. All right, last question. It says that an equilateral triangle can be mapped onto itself after a rotation of all of the following except. So remember, an equilateral triangle, guys, has 3 equal sides. So if we take 360 degrees and we divide it by 3, we would end up with 120 degrees. That's the minimum degree of rotation that you can turn an equilateral triangle and have them be itself. And so 120 would be there. 2 turns of 120 would put you at 240. And then 1 more degree of rotation of 120 degrees would put you right back at 360. And so it's going to be choice 1. You can't turn an equilateral triangle 60 degrees. Okay? All right, guys, I will see you guys in the next day of notes.